lead wings. It's your lead wings thought. Okay, so this is our graph. I think that maybe last time we put a best fit line through it, did we?
Yeah.
There we go, right? Okay, now,
Proceeded to then lose it.
if we look at this thing, if we look at this graph, okay, this really, this axis here, the meaning of this axis is that this really is, secretly, this thing here is actually the photon energy, right? Or I'm sorry, this one here is the electron energy. Yeah? Okay. This axis here, the real meaning of this is that this is really the photon energy. Okay. Really this is photon energy because the energy of photons depends on what? What does it depend on? Depends on the frequency. Double the frequency, double the energy, yes?
Yes.
Ultraviolet is high frequency, it has more energy, it gives you sunburn. Infrared just makes you warm or something like that, right? Lower frequency, lower energy. Okay, so these are different, basically what we did was we took different frequencies of light, and the reason that they're not evenly spaced is that Millikan, when he did the original experiment, had to pick frequencies of light that he could get, and specifically he used spectral lines, right? So that he just took a spectroscope, isolated particular lines. Nowadays we could use a laser. Let's just get 3 or 4 different lasers and shine them on there, right? Okay, but he didn't do that because he couldn't do that, right? So he had to use spectral lines, and that's why they're just whatever they are, right? Okay, so this is very low energy photons. These are more energetic photons. Why didn't these guys, if this is the energy of the electrons ejected from the surface, why didn't these photons eject any electrons at all?
Because there's a work function that they need to get to first, right?
Yeah, you've got to have enough energy to even take it off the metal, right? So if the photon energy is less than something called the work function, it doesn't even eject the electron. The electron just goes, I'm staying put, right? Yeah, gets kind of excited, but then it doesn't leave home. Okay.
So is it light or not?
Say it again.
Is it?
It's light. It's just not energetic enough light. It's too much toward the red end of the spectrum. It doesn't have enough energy to even lift the electrons off the surface, right? Okay. Now, what in general is the relationship between the photon energy and the electron energy? What is this relationship?
Oh, Planck's constant.
It's linear, isn't it? It's linear with a, I believe, a negative y-intercept, correct? Okay. And the negative y-intercept, by the way, would be the work function in, if you extrapolated that down and we had drawn a more clever graph, right? That would actually be the work function in electron volts, yes? Okay. Okay, so there we have it. Now, suppose that we give it exactly, we have this, there's this cutoff frequency there, which to us looks like to be about 525 times 10 to the 12th hertz, right? If we have photons of exactly that energy, the electrons go, and then, I don't know where they go, right? Okay? But if they've got more than that energy, then they actually leave the surface with enough velocity to, and here's the exciting part, in this case, go through, what is it, 1, 2, 3, 4.4 volts of potential, right? They've got enough energy that they can go through that much potential before they are stopped. Yeah? Okay, so then the question is, and this is one of the first questions, and I think on the test, Molly Baker and Katie Ogden got this right. Everybody got it wrong. Everybody had, not only did they get it wrong, but they obviously had no clue how the photoelectric device is used to measure. So let's just, let's go through what would be a good answer, right? Okay. So here is our photoelectric device, right? Here is the light, which apparently they always look like cigarettes, right? We're shining a cigarette on this thing, right? The light hits this thing, and normally, if you're setting up as a photodetector, as soon as those electrons leave, you make this side positive so they accelerate away and you detect them. If the light's shining, electrons flow and you can measure it on the ammeter, right? And if the light's not shining, then they don't flow, so it's like a light detector. Okay? Einstein says, no, take this and reverse it. Okay? Well, this is a variable voltage. If you make it 0, well, electrons still go across. They still are shot across there by the light, okay? And it requires 0 energy to go across. Right? If you make this 1 volt, then they have to have, they're slowing down as they go this way, right? This side is negative, this side is positive. They're slowing down as they go across, aren't they? So if you make it 1 volt of reverse potential, then they have to have how much energy to get across? 1 electron volt of energy. Does that make sense? Or if they make it across, you know that they have at least 1 electron volt of energy, yes?
Well,
They could have more. They could have more than that, but they have at least 1 electron volt, yes? And if you turn it up to 2 and they still make it across, you know that they have at least 2 electron volts of energy. So how would you then determine what the maximum energy is? Would you keep turning the voltage up? You turn it up until what?
No more electrons came across.
Until no more electrons go across. How would you know that no more were going across?
Because the current doesn't go up.
You're measuring the ammeter here, right? The ammeter measures current. It, by the way, counts electrons. Basically, it counts, right? Okay. And then when that reads 0 or thereabouts, right? Okay. Then you have a potential called the stopping potential. It's called the stopping potential because it
Stops the electrons.
stops all the electrons. This is pretty advanced stuff, right? Okay. The nomenclature gets very confusing. Stopping potential, and the way to remember that is that it stops the electrons.
Ah.
That's the way I remember it. It's very counterintuitive. Okay. So again, let's go through that again, right? The light comes on there, it gives the electrons, the energy that it has, by the way, that the electrons have is the photon energy minus the work function, right? Yeah? The work function's a joule, or I'm sorry, the work function is 1 electron volt, and you've got photons that have 5 electron volts of energy, then the maximum kinetic energy they can have is 4. Doesn't that make sense?
Yeah.
Take away 1 for the work function, right? Okay. So you give them energy, right? And the energy that they've got, you decelerate them. You apply a reverse potential, right? And you decelerate them. And basically you just crank that up until you stop them all. When you stop them all, the kinetic energy of those electrons is equal to that voltage,
Or the stopping potential.
right? In electron volts. If it's 4 volts, then it's 4 electron volts of kinetic energy that they have. Okay? So you crank it up, you slowly increase this voltage until you get no current flowing through the current. Okay, so let's go back to our nice graph. Make that graph just a little bit bigger. You have it, right? So this cutoff frequency is the work function. That's how you measure the work function. If we knew the energy of those photons right there, that would be the work function, right? And now, what about this guy? Well, now we have more energy than the work function, so we ejected them, and it took actually 0.4 volts of reverse potential to stop them. Right? Therefore, they had a kinetic energy of 0.4 electron volts. This one, it took 0.7 volts of reverse potential to stop it, so therefore it had a kinetic energy of 0.7 electron volts. Yeah, this is pretty simple stuff. Go study that section. When you look at the review guide, go and study that section, because people generally just have no clue what to say on it. Yeah.
This graph is on the test.
Yeah, same one. Same questions, everything, right? Because, basically I'm giving you a straight score on this test, and the only way to do well on a straight score is to cheat and know what the questions are in advance. And I'm telling you what they are. Okay, I'll show you the little review site. I tell you exactly what question on what pre-quiz, where in the book, where they're solved. In fact, we even made solutions on the wiki for things that we didn't have solutions to that are exactly like it. Okay, so how well you do basically is just how much time you spend looking at the stuff. Okay. Now, we can do. I'm looking at the. I've lost my pencil. Here it is. I lost a very nice pencil too. Okay, I'm going to do number 4. Use an extrapolation of the cutoff frequency to deduce the work function in electron volts. Well, this right here, these photons have just enough energy to just barely release an electron, so that must be the work function, right? Okay, so the work function is HF naught, right? And it says find it in electron volts. So let's do that. Okay, and I'm going to do just that one, and you're going to do the other ones, right? Okay, so this work function, I need the space. Okay, I think that the work function, okay, is Planck's constant, right? So it's 6.626 e to the minus 34th joule seconds, right? Okay, and then I think that cutoff frequency is about 525 times 10 to the 12th, and this is hertz.
The cutoff frequency is where your extended best fit line hits the x-axis.
Yeah, extrapolate, right? Okay?
So you got 5.5 too.
6.626.
Hey Murray, can you
Yeah.
write this on